I welcome you all on this lecture on Matlab as a simulation tool, which is a sub module for the course on modeling and simulation of dynamic system. The thing which I am going to talk today in this lecture, it is a very general term. I will be talking general features of the Matlab, and at the end of about to end of the presentation I will take an example of a second order system, a simple spring mass damper system, and we will see how can we simulate that system using Matlab. During this course, wherever the simulation exercises will be there, often we will be using Matlab as a tool, either directly Matlab or we will be using the Simulink to simulate our system during the future lectures in this courses. So, Matlab is a very popular software used by academician engineers for simulation purpose. It basically means mathematical laboratory, and it is a registered trademark of MathWork. Okay. So, you can get further details about it at www.mathworks.com. It is a general engineering analysis and simulation software. It was originally developed specifically for control system simulation and design engineering, but it has grown over the years to cover many engineering and scientific fields, and these days you will be finding the many toolboxes which are associated with the Matlab. Okay. And with the help of these toolboxes you can do your computations, simulations very easily. As I said, it was essentially developed specifically for control system simulations, okay, to see the behavior of the system and how the system behaves with change in the control parameters, fine. So, this is what was the intention for the development of this software. It is based on the C language and its programming is vaguely C like, but of course it is much more simpler. To start the Matlab software in the Windows or Mac environment, one need to simply double click on the Matlab icon, and upon initiation of the Matlab software, my Matlab window display occurs. The two arrow symbol is the Matlab command prompt, and here the user can type inputs to the Matlab. Okay. So, as soon as Matlab starts, you will be getting these symbols, and here which is the command prompt and where the user can input the commands for Matlab. Now, Matlab provides several windows in the initial interface, say we have the command window, command history, file search path and so on. Generally one can cross out most of these with the mouse and just use the command window here. And the Matlab editor or debugger, which we will be describing later. The Matlab is case sensitive, and which means that the variables say small a and capital A are different. At the command prompt, Matlab can be simply used as a calculator. Okay. So, one can just press enter to see a result, or if you want to suppress some result, if you do not want to see it, then you can just use the semicolon, okay, and followed by enter to suppress a result. So, this is what we can do at the command prompt itself. Say here some basic, although these are very primitive examples, but just to give you an idea. say 4 plus 5, you will be getting answer as 9. So, you can have addition, you can do the multiplication, you can do the subtraction and division, just like what we do in our calculators. Okay. So, this way it can be done. Then there is a function sqrt from which you can find out the square root, or you can have the power. Okay. So, the power is there. So, you can evaluate say 4 power 3 64, or some simple algebraic evaluation also can be done. For example, if I define say a is equal to 5 and b is equal to 4, a plus b will return me the 9. Okay. So, this way using the command prompt of the Matlab, we can do the simple calculations. Now, as when we do programming in any of the programming languages, say Fortran or in C or C++, to make your program readable, we used to put the comment statements. Okay, so that the user who is going to use that program, he is guided by what is actually happening in the program. So, likewise in the Matlab also we can put a comment statement, and that is usually put by putting the percentage symbol at the beginning. Here the percentage symbol at any point in the code indicates a comment, and text beyond the percentage symbol is not evaluated, or it is ignored by the Matlab, and it is highlighted in the green just to indicate that it is a comment statement. As I said in the last slide, the semicolon is used at the end of a line to suppress the display of the line's result, okay, to the Matlab workspace. It is also used to separate rows in entering arrays, vectors and matrices. Okay. So, these things may be in our later lectures, these I will be talking about arrays, vectors and matrices also. Likewise, we can have say the clear command. This command clears the Matlab workspace, that is, it erases any previous user defined variables. As I said, there are many books written on using the Matlab or how to use the Matlab for different type of computation activities. So, my aim here for this 30-minute presentation is just to give you a brief overview of the Matlab and how we can use the Matlab for system simulation purpose. So, it is only to make you to start using the Matlab. So, that is the sole purpose of this lecture. Likewise, there are some other important commands, say CLC, it clears the Matlab command window and moves the cursor at the top. Then the 3 dots, this is basically used to continue a statement to the next line. Then we have a who command, which essentially displays the list of all users created variable names, and whose tells you it is same as who basically, but additionally gives the dimension of each of the variable. Matlab is interpretive like the basic programming language, that is, it executes line by line without the need for a compiler. Matlab commands and functions can be typed right into the Matlab command window. Okay, this gets old fast, especially with the complicated statements, and many times it is difficult to work this way, that every time on the Matlab command prompt you type a program. So, to make our life easier, what is done is that there is a file, that is, one can create a file which we call it as the M file, and on this M file we can write the codes, okay, and then this M file can be executed by just writing the file name in the Matlab command window. Okay. So, this way we can execute the M file. Say put your sequence of Matlab statements, suppose I put it in some ASCII file, say name.m, created with say beautiful Matlab editor or debugger, and of course, this is color coordinated, tab friendly, with parenthesis, alignment, help, and debugging capabilities, all these things are there. And to run the existing M file, say name.m, type only the file name in the Matlab command window, okay, and making sure that the M file exists, of course, in the Matlab file search path. So, that has to be there. So, do not type this .m, rather just type the name of the file. As an alternative, click the save and run button in the Matlab editor to run the M file. This can be done. Using this method, if the M file is not within the Matlab search path, okay, it automatically offers to add your current folder location to the search path. So, this way your current folder location will be added into your search path. To set the Matlab working directory to one that you have used before, click the down arrow at the top of the Matlab window. Okay. The text box displays the current working directory and list shows the recently used directory choices. To browse the new folders not on this list and set one as the current working directory, use the this 3 dots button directly to the right of the working directory. As I told you earlier, here the commands are case sensitive. So, we need to use the lower case letter. We can enter the value of pi is got just by typing the word pi, pi. Now, instead of typing a command at command prompt, this is what I said earlier, a text file can be written and then the command executed by referring Matlab to that file, okay, in the debugging window. Now, if we write a function, say this way, function say sum output is equal to function name and input, okay. So, that type of thing can also be done here. For example, say if I write function y is equal to RMS x, Matlab supplies number of, okay, then I can do that, okay, and Matlab supplies number of toolboxes having collection of M files. One of important activity in simulation is the plotting of the results, okay, in order to see the behavior of the dynamic system. So, to plot the results, we can just say a 2D plot can be produced by using the command plot xy, okay. So, we can use this plot xy command. For example, say if I specify x as say 0, 1, 2, 3, 4, 5 and then I specify y again say 0, 10, 20, 30, 40, 50. So, the plot xy will be plotting this, okay. So, to plot a function whether standard or user defined, use command fplot. So, for plotting of the function we can use just put a f at the beginning of the plot. So, that way we can plot the function. Of course, you have to give the function name and the lim. Lim has to be defined, where lim determines the plotting interval, okay, that is the minimum and maximum values of x. Fine. We can use Matlab also for many operations, okay. Here this picture this slide just shows you to find how can we use Matlab to find the roots of an equation. Okay. So, here suppose I have got a polynomial s cube plus 3s square plus 4 and I need to find out the root of this, then I can just enter here say p is equal to 1 for of course the coefficient of s cube, then 3 as coefficient of s square, 0 for as the coefficient of s and 4 okay, which is nothing but the constant. Okay. And then we can just call the function roots. Okay. So, roots I am putting p and defining this by r, okay, then I will be given the roots. Okay. And I can do the reverse also. Okay. I can do the reverse, that is given these roots I can generate my polynomial. Okay. So, to do that, to generate the polynomial, I have to just write the command or call the function poly bracket r. So, using these roots it will generate the polynomial. So, this is what you are going to get, and basically this shows the coefficients of s cube, s square and s and the constant term. So, this way we can evaluate the roots of an equation, as well as from those roots we can create the equation again. Let us take an example of simulation of a system using Matlab. Okay. Here I will be taking a benchmark problem, that is a simple spring mass damper system. Okay. Let us assume that this is the schematic of the vehicle suspension system, okay, consisting of say stiffness K of the suspension system, damping coefficient B of the suspension system, and say the mass of the wheel is m, okay, and this is subjected to some ground excitation, say some force coming from ground, say Ft. Okay. So, this vehicle suspension system, suppose if I want to solve this using Matlab and if I want to simulate it, and if I want to see the behavior of the system, or the same thing, of course we I can use it for the say finding out the stiffness or damping values in order to get the desired characteristic of the suspension system. So, all those can be done with the help of this simulation exercise. Okay. So, here suppose this is my x direction, that is the direction for displacement of this spring mass damper system, then I can write the equation for this system okay, by just drawing the free body diagram of it. Okay, and I can find out the forces which are acting say in the direction of motion, okay, and those forces I can equate with the mass into acceleration and I can get the system equation. Okay. So, here the conventional way which we use it is this, that if this is my say mass and I have say let us assume that this is moving in this direction, okay, and there is a say force acting from here Ft, then the resisting force from the spring will be of course given by say K into x, where x is this displacement. Of course, I am considering my system to be linear, that is my spring is linear, okay, and spring okay, and spring force is proportional to the displacement. Likewise, I can evaluate the damping force here, and the damper force will be it will be say B x dot, because damper force is going to be proportional to the velocity. Okay. So, from here I can find out the net forces which are acting on the system, and these net forces will be f t minus b x dot minus k x, okay. And this net force I can equate to the mass into the acceleration for this system m x double dot, okay. So, my system equation becomes m x double dot plus b x dot plus k x is equal to f t, okay. Now, for seeing the unforced response, okay, if I want to see the natural response, I can take this f t is equal to 0, okay. So, what I will get is m x double dot plus b x dot plus k x is equal to 0, okay. So, this is the same equation here which has been shown in the slide, m x double dot plus b x dot plus k x is equal to 0, okay. Remember, my aim here is to simulate this system using Matlab, okay. So, just to have a little background of it, I can write the characteristic equation for this one by writing as m s square plus b s plus k is equal to 0, okay. I hope all of us are aware of how these characteristic equations are written, okay. Now, this characteristic equation, as you can see, it is a quadratic equation, okay. Now, I can find out the roots of this quadratic equation, okay. So, this will be S1 and S2, say they are the two roots. So, minus b by 2m plus under root b square minus 4 m k upon 2 m, and the other one will be minus b by 2 m minus under root b square minus 4 m k upon 2 m. So, these are the two roots for this equation. Now, before here if you look at the nature of the roots here, whether they are going to be equal root, okay, or they are going to be distinguished root, or whether they are going to be complex root, that depends on the value of b square minus 4 m k, okay. So, this parameter basically determines the nature of the roots, okay. So, here if b square is greater than 4 m k, then what we are going to have is the case of real and unequal roots, okay. That is, here if we look at this equation, b square greater than 4 m k, what does this mean? This basically means that here b is going to dominate, okay, or the friction is going to dominate, and if friction is going to dominate, the behavior of the system is going to be sluggish, okay, and this type of response is what is called as the overdamped response. This behavior we can see in the Matlab simulation window. Similarly, if the b square is equal to 4 m k, then what will happen, that roots are going to be real and equal, and this is here if you look at this thing, b square is equal to 4 m k, and here basically the friction and stiffness are balanced and yielding the fastest possible non-oscillatory response of the system, and this response is what is called the critically damped response of the system. The third condition could be that my b square is less than 4 m k, okay. Now, in this case you see that b square is less than 4 m k, it means that the stiffness is going to dominate, okay, and when the stiffness dominates, the oscillatory behavior of the system results, and mathematically we can see that by getting the complex roots of the characteristic equation. So, this type of response is what is called as the underdamped response. So, I have the equation m s square plus b s plus k is equal to 0, and if I write this equation into say this form. If I divide the terms of it by m, say my basic equation is ms square plus bs plus k is equal to 0. So, if I divide by m, so what I get s square plus b by m s plus k by m is equal to 0, okay. And this k by m I represent by say omega n square, and b by m I represent by 2 zeta omega n, okay. So, if I do this, my equation will become s square plus 2 zeta omega n s plus omega n square is equal to 0, okay. So, this is this equation which I get. Now, from here if we define this omega n, this is called the natural frequency of the system, and here this zeta is actually what is called as damping ratio. And of course, I can find out this 2 zeta omega n is equal to b by m. So, from here I can find out zeta as b by 2 m omega n, okay. So, this is how I can write it, or I can further write as b by 2 m omega n is under root say k by m, or this will be further written as b by 2 under root m k. So, this is how I can write it. Now, we can get the solution for this equation, okay. We can get the general solution for this equation, okay, and that general solution basically will be say of this form, the one which I have just written here, okay, and it will be of this form. Of course, in the general solution term we are going to have the constant terms, and those constant terms will be evaluated from the initial conditions, okay, initial conditions of the mass. So, say you are given the initial position of the mass and initial velocity of the mass. So, from these two conditions you can evaluate the constant, okay, and one can get the general solution of this system. Now, to simulate this, what is done is that we can create a m file here like this, okay, where we define say this C, and of course, the general solution is written, and after this just to envelop the general solution, the BU and BL are evaluated, and then we plot basically here we plot the general solution y, and we plot the two envelopes BU and BL, and some labeling is done, and the labeling for time and the displacement y is done, and we put legend for omega and zeta for a value of omega and zeta. Now, as I was telling you, to evaluate or to execute this file, okay, it requires certain values, parameters to be specified. So, what is done is that we can specify the initial value here, say y0, then we can specify the natural frequency of the system here, say this one, we can specify the zeta value, and of course, here I can specify the plotting, okay, that is the starting time 0, the final time 10, and the plotting interval as 0.1 second, okay. So, this way I can plot it. So, this is how, as I said, we can provide the Matlab window. We can in the Matlab command window I can enter the values of initial value, I can enter the natural frequency, I can enter the zeta value, and I can enter the time duration, time range for which I want to plot, and I can call the M file as the say the name as unforced one, and this M file can be called for the execution, and you can see that this is what your simulation result is there. Okay. So, here these are the two envelopes which we have seen, okay, in the previous slide, and this one is basically the response of your system. So, this way we can use Matlab, okay, for simulation of our system equation. This simulation could also have been done otherwise, okay. We could have done it otherwise by say writing the second order differential equation which we have got in the say state space form. I would have converted those differential equation in one second order differential equation into two first order differential equation, and then I would have solved those first order differential equations, and then also we could have plotted those graphs. Okay. So, the same thing we will be looking at when I will be talking about the bond graph modeling of the system, and then we will see how can we simulate the system. Thank you.